Good evening. Good evening, everybody. And welcome. Thank you all for coming and welcome to the 7th Annual Janice Pogue Lecture. My name is Harrell Gerstein. I am the Executive Director of the Population Health Research Institute. Just past Executive Director, Salim Youssef couldn't be here this evening because he's currently a bit unwell, but he does send his regards. So it is really my pleasure to introduce Shrikant in just a few minutes, who will introduce our invited speaker. But I think it's appropriate just to remind everybody a little bit about this is our 7th Janice Pogue Lecture, which is in honor of Janice Pogue. Many of us in the room had the real pleasure and privilege of knowing Janice. Janice was an extremely intelligent and quiet, understated individual who really built our statistics department, really built PHRI in a lot of ways. I think she was herself responsible for many of our successes, as our research successes, including several very important methodologic and biostatistical innovations that she helped to lead and disseminate widely. And there's no question that the world of clinical trials and clinical research and methodology has been improved by her contribution. So Janice was our director of biostatistics, who tragically died about 8 years ago at the age of 49 or 50, I'm not sure exactly. And we all think of her every day when we walk by Shrikant's office. Certainly I do. So it's a real honor for us to have set this up. We've had, the A team of lecturers who have come and spoken in her honor over the last 7 years, or 8 years, 7 years, and this is no exception. So with that, I want to introduce Shrikant, who is going to introduce Dr. Harrell. Shrikant.
Thank you, and good afternoon. For those that don't know me, I'm Shrikant Bangdawala, the Director of Statistics. I unfortunately never had the pleasure of meeting Janice since when I came here. But today I have, with great pleasure, to introduce Dr. Frank Harrell as our 7th distinguished speaker in the annual Janice Pogue Lectureship at PHRI. Dr. Harrell received his PhD in biostatistics from the University of North Carolina in 1979, where I had the pleasure to be a co-student with him. He was on the faculty of Duke University for 17 years and at the University of Virginia for 7 years. And then he founded the Division of Biostatistics and Epidemiology at the University of Virginia School of Medicine, and then moved to Vanderbilt University, where he founded the Department of Biostatistics. He is now located at Vanderbilt University. He has taught biostatistics and research methodology to hundreds of physicians since 1980 and has been a mentor or co-mentor to several physician investigators. He's an associate editor for Statistics in Medicine and serves as a statistical advisor to the U.S. Food and Drug Administration. His specialties are development of accurate prognostic and diagnostic models, model validation, clinical trials, observational clinical research, technology evaluation, quantifying predictive accuracy, missing data imputation, pharmaceutical safety, flexible Bayesian design and analysis, and statistical graphics and reporting. You could call him the Renaissance man of statistics for his breadth and depth into statistical methodology. He has worked in cardiovascular research and statistical computing for 50 years and is the author, I forgot to bring it, the Popular Research Modeling Strategies, which is sort of the Bible for all regression courses. He's done a lot of programming in R packages. He has free online text. He is well known for his giving of himself to help other statisticians around the world. understanding difficult and complex statistical methods. I remember him when in his career, he developed a macro that he then proposed to SAS that was at the early stages of SAS, and that macro in SAS is what's now PROC PHGLM, and that's what everybody uses to do Cox models. Just wanted to remind you that he will also be given a seminar tomorrow at the HEI department on Bayesian thinking with a variety of examples, how different it is from statistical traditional analysis. But today, he's going to be giving us a lecture on modernizing clinical trial design and analysis to improve efficiency and flexibility. So let's welcome Dr. Harrell.
Thanks for the wonderful introduction, my former classmate, Shrikant. I'm deeply honored to be chosen to give this year's Janice Pogue lectureship. I was not fortunate enough to have ever known Janice, but I know her by what people say about her. And people talk about how respected she was, how thoughtful she was. She was beloved and she was admired. Being struck down in the peak of one's career is unimaginable. And someone who had such influence in making research better in so many ways. Of course, we don't know it was the peak of her career. She might have ascended to even greater heights. Unfortunately, we'll not know. It's so unfair, so tragic. But again, I'm just deeply honored to be doing this in her name and in her memory. So I'm going to talk about some opportunities for making things more efficient in clinical trials if we're willing to accept change. And I find that accepting change is one of the toughest things for people to do. And I've been trying to study for years why that is. But part of the reason is you learn a set of tools, you learn a set of skills, you gain knowledge, and you love using those. And if something new comes along that requires you to do something in a totally different way, there's kind of two reactions you can have. One reaction is to say, this is a great opportunity because I love learning stuff. It's fun. The other opportunity is to say, I'm busy. And unfortunately, the busy one tends to win out too much of the time. But I'm a weird enough person that if I don't learn something new every single day, I get sleepy during the day. And so it has to be something. It may be a statistical method, even reading an abstract of a new statistical method, learning a new statistical computing tool, or new graphics way to present data, has to be something. So I've always loved the idea of learning new stuff. And so think about that as we talk about how clinical trials could be done drastically differently than they are now if we're willing to do things in a new way. And one of the other things to remember, just setting the big picture, is when you see another way to do something, you don't have to say that everything you've ever done is wrong or bad. All you need to say is onward and upward. There's new opportunities out there, and we don't have anything to apologize for in our last 100 years of the way we practice statistics, but it is time for change. So a little bit of background. Can you act like a physicist in the clinical trials and clinical research and public health research world? So the way physicists operate is they experiment until they have an answer. Sometimes they give up because they run out of energy, maybe out of money. Some answers don't ever come. You know, we have so many things we're trying to find out about dark matter for so long, and it's tough to figure that out. But can you really act like a physicist and be a scientist? And I would say absolutely. I think physicists are terrific scientists. And the fact that they can not have experimental design the way we do it with sample size calculations is only to their advantage. It's nothing bad. And because we don't act like physicists, though, we almost never do fully sequential research like physics does. And if you think about what you can do with fully sequential knowledge acquisition, through data, it can be more useful than doing things in a very fancy or adaptive sort of avant-garde way. There are times when you do adaptive designs and they're really what you need, like you're doing dose finding. You might be studying 10 different doses, and you want to adapt until you hone in on the best dose for a safety efficacy profile. But in other cases, adaptation, even though it's touted in many statistical circles as being kind of the great savior, is not as good a thing to do. It's not as beneficial as doing simple things like sequential testing in the majority of cases, not always. So what keeps a researcher from collecting data until there's sufficient evidence in one direction or another, or until she runs out of time or money? So what are the obstacles to doing that? Well, traditional frequentist statistics is a major obstacle in this regard. And then fixed budgets are the other major obstacle. I can't say which one is a bigger obstacle. They're both big. And so governments grant budgets for projects, and the projects almost always have a fixed duration. And if you have a 5-year funding to do a clinical trial, even if the treatment is very ineffective, it's very rare for a researcher to say, after 1 year of data, we have overwhelming evidence of ineffectiveness of this treatment. I'm going to give the money back for the last 4 years. So that doesn't happen. And likewise, the government doesn't say, well, you're at the end of the 5th year. What you're doing has so much promise and it wasn't quite establishing evidence, but it deserves extra money. But until we're able to do things like that, we're going to be stuck. And this also leads into discussions we could have about platform and basket trials and other ways to get around this, which I'm not addressing today. So wouldn't it be more logical to direct more resources to promising studies and direct resources away from unpromising studies? So an unpromising study would be one that has a high probability of inefficacy, or if there is a efficacy, it's trivial. So you have a new blood pressure drug that's lowering blood pressure on the average about 1 millimeter of mercury. That's really not clinically relevant. And so if you calculated a Bayesian probability that the improvement in blood pressure is less than or equal to 1 millimeter of mercury, and that probability was very high, that's a great reason to quit. You'll be amazed how early you could stop studies using that philosophy, and I'll talk more about that. And so why does traditional statistics keep our hands tied? And so these are a couple of questions to ask yourself to see if you really are committed to tradition or whether you're open to something new. And when I say something new, Bayesian statistics came out way before the statistics we use now, back in the late 1700s, but Thomas Bayes did not report on any of his research. He left notes for his good friend, Thomas Price, I believe, found the notes in his study after he died. And so he didn't have any advocates during his lifetime. And that's part of the reason the method wasn't used more. It also didn't have a Ronald Fisher going around the world giving lectures. So would you rather know the probability of a positive result when there is nothing? So the probability of getting impressive data when the treatment does exactly nothing. It doesn't hurt you, it doesn't help you, it does exactly nothing. So when the treatment is ignorable. So we're trying to learn about the likelihood of getting impressive data when there's nothing. So that's the probability of a positive result when there's nothing. But what is more relevant by far to decision-making is the probability that a positive result turns out to be nothing. Now, those sound like similar words, but those words could not be more different in their implications. It's night and day. So the probability that a positive result turns out to be nothing means the probability that a drug that you think is effective because of data is actually not effective at all. So in other words, the probability that you've made a mistake. And so another way to phrase this, are you interested in how surprising is our data if the treatment has no effect? Or are you interested in the probability of all possible levels of efficacy? So if you were interested into this in the second of those two pairs of things, you have Bayesian tendencies. And if you like the first of each of the pair, you like the frequentist status quo, and you probably want to stick with it. And so the frequentist status quo puts a lot of emphasis on things like p-values. And a p-value is the probability that the data are, you would get data more impressive than our data if the treatment is ignorable. That's the most frequently calculated p-value. And it's really important to emphasize that word more, as I've bolded there. So it's not the probability of getting results like what you got. It's a probability somebody else will get data more impressive than yours if your null hypothesis is true for them. So you think about what that actually means. It doesn't mean very much. And whenever your outcome variable is continuous, the probability of observing exactly what you observed is 0. So that's why I put more here. In tomorrow's talk, I'll give an example with a discrete outcome where I show how a p-value is decomposed into two things: the probability of getting what you got, plus the probability of somebody else will get something more extreme than what you got. But in continuous outcomes, we don't need that. So the probability that somebody else's data will be more impressive than yours, if your null hypothesis is true for them, is the basis of null hypothesis significance testing. It sounds silly just to enunciate it, because it is silly. Now, if you like the second way of doing it, you have Bayesian tendencies. And I think I remember this when we were in school. You know, I was told by my professors that Bayesian methods are bad. And I think I even remember in the Daily Tar Heel newspaper one time, somebody put an anonymous ad in the classified saying professor and named a name is Bayesian. Like it's a rumor they were trying to spread in Chapel Hill. So with posterior probabilities, you're computing probabilities about the unknown. And what's the probability that some unknown treatment effect is greater than C, given the data, given the state of prior knowledge before you collected the data? So that's a probability that is a direct probability. That's a probability we're trying to make a statement about the unknown based on what's known. So we're working in the direction of uncovering hidden truths. We're not so interested in if you assume a hidden truth that's unknowable, what's the likelihood of observing certain things? So to make it real, you might say, what's the probability that the drug is effective in any blood pressure reduction? Or you might just as easily compute the probability of a non-trivial reduction in blood pressure, or the probability of similarity. So you define a region of practical equivalence, ROPE, and you calculate the probability that the difference in blood pressure between the groups, the unknown difference in blood pressure means, is within the interval of the equivalence region. So all of these things are calculated using the same fitted model in the Bayesian world, and they're all easy to calculate. So that leads into discussion of power and sample size. What's the most common outcomes of a clinical trial? The number one outcome of a clinical trial is insufficient patient recruitment. So in the US, the median sample size for oncology trials is 0. That's actually true. The median is 0. In other words, half of the oncology trials opened in the US never recruit a single patient. Now that's kind of extreme, but we know that in everywhere we have trouble recruiting, and that's one of our biggest challenges. Even if things are going well, an epidemic may come up, and all of a sudden you have great difficulties recruiting. But the second most common outcome of clinical trial is an equivocal result. Equivocal result is something that we should be very sad about. And if you look at the New England Journal of Medicine and JAMA, Lancet, British Medical Journal, they're not sad about it because they'll never say that it actually happened. They will just say the results were not significant. They will often say, every week you'll see one of the big journals say this in a paper, committing the error, absence of evidence is not evidence of absence, by saying that this trial showed the drug doesn't work, when the trial did no such thing. But they're not willing to be sad. They're not willing to say that the money was spent, and we know nothing now that we didn't know before the money was spent. But that is a very, very common result. At the planned sample size, the results are not, quote, significant. And what usually happens is at that point, you look at the uncertainty interval, and for most studies, it's very wide. And so you ask yourself, what do you know now that you didn't know before? This is in extreme. If you ever work with animal experimenters that have 3 dogs and they don't find statistical significance, and you calculate a confidence interval from 3 dogs, and it's like plus or minus infinity. And you ask them, what have you learned? So they may have learned how to euthanize dogs very efficiently, but they may not have learned much else. So you're not learning about the effectiveness of a treatment when the confidence interval is this wide, but you have learned that the money's spent. So what are the most common causes of equivocal results? Over-optimistic power calculation. I had an experimenter come to me at University of Virginia saying, I need to know how many mice to have to detect a 25% reduction in some physiologic thing. And I told her she needed 20 mice. She did the budget calculations and was shocked. These were very, very expensive mice. And she said, you know, I messed up when I talked to you. I should have said, we want to be able to detect a 100% reduction. Those were her words. And I don't remember what I said. I was kind of shocked. But I think I said something like, you know, why do you ever use more than 2 mice then? So what happens is we use effect sizes that are greater than clinically relevant. And I tell young investigators that when you're determining the effect size, you need to go in isolation. You can't talk to a budget person. If you talk to a budget person while you're choosing the physiologic effect size or the clinical outcome, odds ratio, whatever, you know, you're engaged in bad practice. This problem, though, persists to this day. And if an effect is only clinically relevant, let's say you only reduce mortality by 10%, and you powered the study to detect a 25% reduction in mortality. So if it's only clinically relevant, you're left with 0. So you power a study to detect a miracle, miracle doesn't happen, you're left with nothing whatsoever. And how often have you seen that in your practice? I see it far too often. Another culprit is a fixed sample size. Why do we think of the sample size as the only thing in our calculation that's really not a random variable? The sample size is a random variable if there ever was one. It's the thing we're most uncertain about. It should be thought of as a random quantity. It's like an outcome variable more than it is like a constant. So we lose power in the belief that alpha is something that should be controlled. That's another culprit. So once you decide that you want to spend your alpha, and first of all, you have to realize that when you say alpha is type 1 error rate, it's not a rate, it's not an error. It has nothing to do with rates, has nothing to do with making an error. It is just type 1. So I've changed my language whenever I write something. It's type 1 assertion probability, because that's exactly what it is. It's an assertion probability, has nothing to do whatsoever with making an error. But if you believe that you should control alpha because you're taking multiple looks, you're going to become very conservative. And you're not going to look very often. Another cause of equivocal results is an insensitive outcome measure. This happens in all clinical fields. I've seen some real doozies where, like in orthopedics, somebody might really care about bone mineral density, but they dichotomize this beautiful variable and do some kind of responder analysis and cut out most of their power. But this happens in cardiovascular very often, that insensitive outcome measures are chosen. Another common outcome is you get to the end of the study and your confidence interval might be decent, but you just have little evidence that the treatment actually works. So you've had a successful study. But why did it take going to the planned maximum sample size to come to the conclusion that something didn't work? It almost never requires going that far. So I do a lot of work with FDA, and some of that involves work with rare diseases. And in rare diseases, the thing that happens that is so shocking to me is rare diseases need more efficiency than anything you ever get involved in. You have to be so efficient in the design and the analysis and the outcomes. And rare disease researchers are simply not doing that. They're making all the mistakes in rare diseases that we see in common diseases, and the sample sizes in rare diseases, such as a study I saw with 24 patients where they had a nice continuous outcome that they dichotomized and did a responder analysis. They made the 24 patients have the effective sample size of about 10 patients when they did that. That's criminal. Criminal. That's that's a data rights violation. So in the frequentist world, you need a final sample size to know when your alpha is spent. So that's part of the design challenge here. And then fixed budgeting also requires a maximum sample size. And then everyone who's ever done a sample size knows it's voodoo. It's just plain voodoo. People call it the sample size samba. I forgot who came up with that terminology, but it's so true. It's just a dance. And you have all these compromises until everybody's happy or pretends to be happy. And so we make up everything. Alpha is arbitrary, beta is arbitrary. How many of you are still doing study designs where you choose beta as 0.2? Do you ever fuss at the investigator? Do you go along with that? I'm looking at you now. Do you ever, if you use a 0.8, do you ever tell the investigator you're valuing a false negative 4 times less important than a false positive? Why do you value that in a 4-to-1 ratio? Makes no sense. But we just don't know enough to do an accurate sample size calculation. So how many people know how many patients you need to estimate sigma if you have a continuous outcome and you need to estimate sigma to go into your power calculation? Anybody want to take a guess? Well, definitely a minimum of 2. So it needs 70. So you have to have 70 patients to estimate sigma well enough, and it needs to be a relevant sample. A lot of people are doing power calculations with estimates of sigma, which is critical in the power calculation. That's not accurate enough. So you might get the study going and need to revise the sample size calculation because the standard deviation across patients is bigger than what you planned for. And why do you think the sample size should be fixed and not updated? I mean, the sample size is actually a premature calculation. So the physics approach, as I mentioned, is you experiment until you have the answer. There's nothing wrong with that. So do you need a sample size calculation at all? Yes, if the budget's fixed. We need to relabel what the sample size is. It's a maximum allowable sample size for budgetary or practical reasons. It's nothing to do with data. If you're using a Bayesian sequential design, you don't need a sample size in any sense of the word, because Bayesian doesn't have anything like alpha, so there's nothing to spend against like you have. Just like if you ever heard of sample size re-estimation, everything seems to be going okay, and then something goes wrong, you realize the study's not designed right. You need to stop and do a frequentist sample size re-estimation calculation, and then you need to take a hit for the fact that you've already analyzed the data once And you find out that when you do your sample size re-estimation, when you get to the final analysis, you have to discount the new patients who are added because of an alpha penalty. So you might add 50 new patients, but you only weigh them in the analysis as if there were 20 patients. That's what happens with alpha spending. You're actually getting 50 new patients that you can't use them. You can only use 2/5 of them because you have to control alpha. It doesn't make any sense. So with Bayes, if you want to extend a study, you can do it really easily. There's nothing in the Bayesian formulation that you could even think about penalizing, even if you wanted to. So it's logical to recruit more patients if a result is promising but not definitive. So let's say you have a probability of benefit of a drug or a treatment between 0.7 and 0.95, looking promising, but we don't know enough yet. Justification for keeping that yearly budget coming, or whatever mechanism you have. What happens with Bayes is when you have cumulative analyses, every new analysis is more complete than the previous, has a bigger sample size, longer follow-up. And the only thing you need to know is that last analysis is obsolete. So when something is superseded, just like you're watching a football game and somebody tells you, don't get so excited about the score at the end of the third quarter because your team was behind at the halftime. I'm going to discount the score now at the third quarter. And nobody would make any sense out of that. So the new score supersedes the old score, makes it obsolete. So the only thing you have to do with the Bayesian paradigm is to throw it away. The fact that you looked before is of no consequence anymore. And I'll talk more about that tomorrow. So alpha is a type 1 assertion probability, which is essentially the probability of getting a p-value less than 0.05 if the treatment is ignorable. So that's the usual null hypothesis testing setup. It's not the probability of making an error in acting as if a treatment works. It has nothing to do with that whatsoever. It's the probability of making an assertion of efficacy when any assertion of efficacy would be by definition wrong. So you imagine this stream of experiments all produced by a treatment that has no effect. How often will one of those experiments have impressive data in that stream of experiments? That's all it is. So the probability of making an assertion when any assertion is by definition wrong. Any assertion of a positive effect is by definition wrong. That's all it is. So you can see if you ask on one side, what is alpha and what is a decision error? Those two don't intersect each other. So a decision error is a totally different thing than the probability of triggering an assertion of an effect. Alpha does go up when the number of data looks goes up. Alpha includes the probability of things that might have happened. So even if you have strong evidence at a given time, our design had the possibility of showing evidence at an earlier look. And because it had the possibility of showing evidence at an earlier look, even though it didn't, we need to modify how we view the current evidence. So I was a consultant to a study where they were trying to control alpha at 0.05, and they had an early look. It was a really dangerous treatment. They had an early look, and they figured they were going to have a hard time randomizing patients. And I wrote this up as a blog article because the treatment was to put a bronchoscope down somebody's windpipe and to use radiofrequency ablation to burn away some of the tissue for patients that have refractory angina, refractory asthma, who were going to the emergency room 4 times a year. So actually open the airway using burning tissue. So half the patients got a sham procedure where the bronchoscope went down and was turned the same protocol and was left down the same length of time. And it was a perfect design. And the company that made the device thought they would have great difficulty recruiting. They had to turn people away. People were coming to sign up for that study who were desperate with refractory asthma in record numbers. They came so fast, they had no time for an interim look. But the pre-specified statistical plan said we need to adjust for an interim look. That never happened. And when you adjusted for it, they didn't meet the efficacy target, so-called negative primary endpoint. How does that make any sense to call a study that had a probability of 0.982 that the treatment was efficacious, to call that a negative study because you planned for a look that didn't happen? And that's how you calculated alpha. Makes no sense. So asking one to compute alpha for a Bayesian design is like asking a poker player who wins more than $10 million a year to justify his high ranking in the poker world by how seldom he places bets in games he didn't win. I think the poker world would look at that with great amusement, and they'd say, you know, we tend to judge the poker players by their winning percentage and their winnings. What you're judging them by, this alpha thing, you know, we don't see the relevance of that. And they'd be right. So you get conservative when you adjust for alpha when there's multiple data looks. And the way Bayesian sequential designs work, the more often you look, the lower the expected sample size. So if you look after every patient, you'll have an expected sample size of the study that is lower than if you look every 5 or 10 patients. So the more often you look, the more opportunity you have to stop early for various reasons. So your expected sample size over all those sequential looks will go down. In the frequentist world, you really reach kind of a plateau, and because it has to be more conservative. So what should we control? We should control decision errors. A decision error is all that matters. You want to know when you make a decision, is that decision valid or not? We don't care about long run operating characteristics in somebody else's stream of experiments anymore. So a decision error is a probability of being wrong when you act as if a treatment works. In other words, a probability you made a mistake. That's why I never use the word error when I talk about alpha. It has absolutely nothing to do with errors. So the probability of being wrong and acting as if a treatment works is 1 minus the probability that the treatment works. And that's controlled by the prior distribution and the data and the statistical model and the outcome variable and the sample size. All of those things will go into your evidence calculation. So for example, if you said that we have a 0.96 probability that a treatment is benefiting patients because the hazard ratio is less than 1, the probability the hazard ratio is less than 1 given the current data and a prior distribution is 0.96. That means the probability of inefficacy or harm is by definition 0.04. So you just 1 minus the probability of something good is a probability of something bad. So that is your error probability. It's built into Bayes. Whereas with p-values and alpha, they don't give you anything remotely like this. So you're controlling the reliability of the evidence at the decision point. When you say alpha, alpha is something you calculate before the study begins. Alpha is not a function of data. It doesn't use data anywhere in the calculation. What we want to know is once you have data, are you getting misled? We don't care about design characteristics, long-term operating stuff. The pre-study tendency for data extremes under an unknowable assumption is what you're getting with the frequentist world. You assume null hypothesis. You don't know if that's true or not. You're assuming something you can never know to calculate the probability of something you shouldn't care about. That's a lose-lose proposition. I'm glad the frequentists out there can laugh about this. So How do you gain power with a Bayesian sequential approach? You gain power by not having an alpha penalty, because forward probabilities don't need to be penalized for context. The earlier looks are obsolete, they're just dropped. And you gain power by being directional. So when you think about a two-tailed p-value for a mortality test, you're penalizing for multiplicity. You're penalizing for the chance that you might want to claim that this drug kills people. You're going to write a different article, and now you're going to write it for the US Army to use in combat as a weapon. And you're going to have a penalty for two ways, efficacy or killing. You've got a penalty for multiplicity with a two-tailed test. We don't have talks like that in the Bayesian world. You want to know the probability that treatment helps people. And I'm not going to want any other thing to come into that calculation. Like I might want to claim that it's good for euthanasia. I'm not going to do that. So in the Bayesian world, you allow for infinitely many data looks, and then you can borrow information. And this is super important, because how many trials have you designed where you say, well, there might be a treatment by age or treatment by sex interaction, and I don't know what to do with that in my statistical analysis plan, and I don't know whether to include that in the main analysis or to put it as a secondary analysis. And if I include it, do I test the treatment effect with 2 degrees of freedom, or do I test some sort of average over the sexes as if the interaction wasn't there? We have all these design questions we never really know how to answer. The Bayesian world would say the interaction is half in the model, it's half out of the model. The degree to which it's in the model will be the prior distribution for the interaction effect. And so you can specify a prior, which says how much borrowing you're going to have to inform the female efficacy estimate from the males. That's just a specification of a prior. So you're going to give the interaction effect like a half of a degree of freedom, not a 0 or 1. Outcome variable is another problem with efficiency of clinical trials. So time to a binary event is the lowest information outcome. The only way to make that lower information is if the event never happens. So you have a binary event and nobody dies, you would have no information for estimating treatment effect. And so we're not distinguishing different grades of outcome. So when you do things like major adverse cardiovascular event, and you have myocardial infarction as one of the components, we're not distinguishing a small myocardial infarction from a large one. This is really a problem. Cardiology, I've been bugging all my cardiology colleagues about this for ages. And some of them are very concerned about this, but not many people have done something about it. So we need a measure of severity or size of the infarct that includes the location. Is it in a region that's threatening the pumping ability of the heart or what? If you have time to first event and somebody has a non-fatal heart attack and a couple of months later they die, the death is completely and utterly ignored. How does that make any sense clinically? And so because of minimum information and time to a binary event, you need 462 events to have the ability to estimate a hazard ratio to within a factor of 1.2 multiplicative margin of error or fold change error. And so to get 462 events often requires following 6,000 to 10,000 patients in a disease that's not imminently fatal to them. If they have more chronic, mid-level heart failure, you have to follow a lot of patients to get 462 events. If you had a continuous outcome, it's hard to equate those to each other, but if you had a continuous outcome with a 0.2 standard deviation, you need 384 patients to have the ability to estimate the effect. And if you do a crossover study, you only need 96 patients for that setting. So you can see the efficiency comes from the resolution of the outcome variable, as well as the design. Can you do a crossover design? We're not often able to do that, but they can be quite magical. But you can see the difference between this and this, because this may entail 6,000 patients to achieve that number of events. And as the number of events goes down, the time into the event is less and less informative. So if you do a Cox model with a rare outcome and your test is a hazard ratio, that will not have much more power than just a 2x2 table. The time becomes irrelevant because it becomes much more relevant as the event frequency goes up. So general outcome attributes, timing and severity of outcomes need to be captured. And we need to handle terminal events such as death, non-terminal events such as myocardial infarction or stroke, and recurrent events such as hospitalization. And I guess MI and stroke could also be recurrent. And so the idea of increasing power is to break ties in the outcome. So anything you can do in statistics to break ties is always advantageous. You know, even if it's an exposure variable that you were making binary, if you can make it continuous. But if you can make your outcome variable continuous, it makes even more of a difference. So having more levels of Y the better, and you get the maximum power when there's only one person in each category of Y. That would be like you have a totally continuous outcome variable. That gives you maximum power. So what is a fundamental outcome assessment? I claim that it is in a given time period, which may be a week or a day, depending on your situation, what is the severity of the worst thing that happened to the patient in that time interval? So if you can capture that, in other words, you can turn the event timing into a longitudinal study. And on a given day, what's the worst thing that happened to the patient? You're going to get something that is clinically interpretable, has superior power, far more interpretability than most timed event analyses, and it handles competing risks, recurrent events automatically, and it handles absorbing states or terminal events. So most clinicians are in agreement about what kind of outcome is worse than one other. And you don't have to ask them in this framework, is an early heart attack worse than a late death? You never have to ask them that in a multi-state model. All you have to say is a heart attack better than a death? And is a stroke worse than a heart attack? And then how far can you carry it, like levels of stroke? So those are the things you need to base the analysis on. There's a lot of consensus about these things. The spacing of the outcome categories is irrelevant. And so you might do well to call your categories A, B, C, D, E instead of numbers. I use numbers for convenience, but we're not using the spacing of those numbers in any calculation we're about to do. You can grade events, and you can also code common co-occurring events as worse. So if you had a number of people that had both a heart attack and a stroke in a given week, you could just call that as worse than either one and make that a new category. So we're building up towards an ordinal longitudinal model. And from an ordinal longitudinal model, where you have ordinal states on a given week or day or month, you can use that one model to get all kinds of estimates, such as expected time until something happens, like we're used to doing. But you're doing that not with the raw data. You're not calculating time from the raw data, you're calculating it from the longitudinal model. The expected time in state. So what's the expected time in the hospital for a patient with congestive heart failure? Expected time in the hospital over a period of 6 months. What's the probability of something bad or worse happening to the patient over time by treatment? This is the fundamental first thing you would estimate. And then we have this partial proportional odds model that can allow the treatment to affect different parts of the outcome differently. This is something clinicians are racking their brains over. I don't know if this treatment effect is being driven by heart attack or by death. And I do all this ad hoc informal analysis to try to figure that out. Well, with this model, you would do a formal analysis that says, what's the evidence that the treatment effect on death is similar to the treatment effect on heart attack? That's a very formal parameter that's in the model. Oops. And this also handles partial information. So every time you're assessing the patient status, that assessment can be interval censored or left or right censored. And I'll show you an example of that. So here's an example where you just had dead or alive. And so normally you would do time to event when you have a single event and its absorbing state. So time to event analysis will work very fine. What does it look like for longitudinal? Well, if you had weekly assessments, you've got 3 zeros for somebody who's followed 3 weeks and who didn't have the event. Somebody that has a death at 2 weeks, their data looks like this. And if you calculated the odds ratio from a longitudinal binary logistic model, that will equal the hazard ratio from a Cox model. So you can reproduce to like 3 decimal places. You can reproduce the hazard ratio from an odds ratio. So this would be overkill, but it leads to what we really need. So suppose our daily status, instead of doing a competing risk analysis that we have great difficulty interpreting, we're going to say that your status is 0 if you're at home, which is our best outcome. 1 if you're hospitalized, 2 myocardial infarction, 3 is dead. So somebody who's hospitalized at 3 weeks, rehospitalized at 7 weeks, heart attack at 8 weeks, and stays in the hospital, and the follow-up ends at 10 weeks, is going to look like this. So that's hospitalized, they're back home, hospitalized again, heart attack, hospitalized, hospitalized. That's your longitudinal record. That's your raw data. So whenever we're doing time to event analysis, we're not actually analyzing the raw data. We're not respecting the raw data. The raw data comes from current status. Doesn't come from gap times, time to first event. That's not raw data. This is raw data. First rule of a statistician is analyze the data in the rawest form possible. Even if you're into bioinformatics and genomics and everything. You know, if you could analyze the raw data, you would do a better job than analyzing pre-processed data. It's just very hard to do. So here we're extending it now. So the category 0 to 6 is quality of life, and 6 is the worst, 0 is the best in this scale. 7 is heart attack, 8 is stroke, 9 is dead. Quality of life is not assessed in the 3rd week, but in the 3rd week, we know the patient is event-free. So we know something there. So this is not a multiple imputation problem. This is a partial information problem. So the 3rd week, we know that their outcome is less than 7 because they're event-free. So their outcome is between 0 and 6. So when you're calculating your likelihood function, you would put in the probability element is the probability of being less than 7. And then you calculate the log likelihood. That's how you handle censored data. So you don't have to do any imputation. Here's somebody that had that same missing quality of life assessment, but we didn't know their heart attack status way out here. So when you look through what the data mean here, you'll know that at that week, their outcome status is a quality of life 5 if they didn't have a heart attack, and it's a ordinal outcome of 7 if they did, because that's what heart attack is coded at. So you'll calculate the probability that the ordinal variable is equal to 5 or 7. That goes into your maximum likelihood estimation, no multiple imputation. And then what if you had a continuous response variable like kidney function measured by serum creatinine? You might have 200 levels of kidney function. And then if the person needed dialysis because of acute kidney failure, that would be a 201. If they died, that's a 202. So you can handle that kind of extension. So we can use a partial or proportionalized ordinal logistic model with covariate adjustment. The longitudinal within patient correlations can be handled very easily with a Markov process. So with a Markov process, you're saying, given the previous state the patient was in, what's the probability they'll be in some new state? And so the previous state becomes a covariate, just like age or treatment. The previous state is indistinguishable from a baseline covariate. So the way you handle correlation patterns with Markov processes is so much easier than using random effects, and it will usually fit the data better than what random effects assume for the correlation patterns. And random effects models will not handle absorbing states at all. So if you try to put death into a random effect longitudinal model, it just simply doesn't work. This generalizes the binary logistic model, the Wilcoxon two-sample test. It generalizes the Cox model. Those are all special cases of this data layout. There's no distributional assumption about Y for a given patient, and the numeric spacings of the Ys, like 0 to 9 or whatever, are not used in the actual calculation. You just need the ordering. So we get an odds ratio interpretation. We get the probability that a patient on treatment B does better than a patient on treatment A. So what we get out of a Wilcoxon test, you can get that out of an ordinal logistic model. If you get an odds ratio from a proportional odds model and you use this formula, you get almost exactly the Wilcoxon statistic or C index. So this is the probability that a patient does better on treatment, a randomly chosen patient does better on treatment B than treatment A, is a simple function of the odds ratio in a proportional odds model. You can calculate the probability of having a certain outcome or worse as a function of time or treatment. You can estimate the time gained in good states, which to me is a really great clinical readout. You have all these outcomes going on, but some clinician says, what really matters is a patient able to stay out of the hospital, avoid a heart attack, stroke, or dying. So what's their mean time well? And how does that mean time well differ between treatments? Very easy to get with this model. So this is what it might look like in a proportional odds model. The probability of being hospitalized or worse over time if you're on treatment A versus B. The probability of having a heart attack or dying if you're on treatment A versus B. These have to be lower than that. These are cumulative probabilities that include these. And this has to be lower than those. So under proportional odds model, you'll get a same kind of effect over all levels of the outcome. And this would be a good way to display it. And there's one other way that may be even better. So if you look at this randomized trial of vitamin D for treating patients with acute respiratory distress syndrome, one of the multitude of failed vitamin D studies in the world, we have an ordinal outcome collected each day for 28 days with almost no missing data. And so we have a version of this data set for teaching purposes on our website. It's just an amazing data set. So this is what the first 14 days of data look like when you have a longitudinal ordinal model. And you can see we have placebo vitamin D each day, and then the proportion in the various outcome states. So the lowest category is dead. You notice that's always increasing because it's an absorbing state. The other states can go up and down over time, but death has to be one direction. This is having being on a ventilator or having acute respiratory distress. This is being in a hospital, but not on a ventilator. This is being at home. The clinicians love these stacked bar charts, and we've extended this to the case where your ordinal outcome has like up to 74 levels with different shades of colors and zones of colors. So there's a good example of that in a Lancet article. But this is the presentation for a discrete ordinal outcome variable. I think it's very clinically relevant. This shows the efficiency of an ordinal analysis versus just measuring the patient's outcome at 1 day. So if you had to measure it at 1 day, day 14 in the middle of the follow-up is as good as any. And so if you measured the patient just at day 14, you're going to have a relative efficiency of 1. But what if you measured the patient at 2 days, 3 days, 4 days, up to all 28 days? So this is the relative efficiency of a longitudinal model that uses daily data versus just picking one ordinal outcome for day 14. You can see the efficiency raise here is stunning. So by the time you get to 28 assessments, every patient is contributing the information of almost 5 patients. So one patient measured 28 times has the same statistical information as 5 patients measured 1 time. So you're taking into account the correlation structure, but the power gains from this approach are very impressive. So here's an example A lot of people do time to event analysis with acute diseases like COVID. It's a defective outcome in every sense of the word. It has so many problems. One of the chief examples of a problem is 4% of the patients who recover from COVID who were hospitalized unrecover and have to go back to the hospital. So if you unrecover from COVID, the analysis completely ignores it. If you have ordinal status, you can go up and down. Everything's handled. And then you have a power loss. So the time to event analysis in this simulation had a power of 0.79. If you just calculated the event-free days with death as a -1, which is used a lot in ICU research, you get a very poor power. And if you use the full information longitudinal model, you get a superior power. So it can make a real difference in your sample size calculation. So we need to use some general principles for choosing outcome variables. This can have the biggest bang for the buck of anything you can ever do in designing a trial, more than Bayes even. So you increase power by breaking ties, you get close to the raw data, you make the outcome measure relevant to patients, you respect the timing and severity of outcomes, and if you want to go so far as to do risk-benefit trade-off, you can include safety endpoints in the efficacy ordinal outcome. Most clinicians I've talked to are not ready to do that, and there's some reasons to keep those separate. But you could do it. Then there's covariate adjustment. This is something that I think most people are pretty familiar with. Covariate adjustment is one of those things that's a free lunch. You can do a covariate adjustment and do everything wrong. You might have a nonlinear age effect and you model it as linear in your covariate adjustment. You might pick the wrong variables to covariate adjust, and it still is a big plus. So covariate adjustment is so valuable that you can do it wrong and still have a major power gain. John Tukey wrote a paper to that effect in the Journal of Clinical Trials many years ago. And so what you're doing is helping with the extreme outcome heterogeneity within a treatment group, which randomization has nothing to do with. So adjusting for strong baseline prognostic factors increases power at no cost to anyone. So the primary analysis should always be an adjusted analysis because what you're adjusting for is that patients are different from one another, even if they're on the same treatment. So for example, I've seen studies of COVID that did not take into account that older patients die sooner than younger patients. They treated a 90-year-old with COVID the same as a 30-year-old. That makes no sense from the data. So age will be a covariate there. 6-minute walk test, people that have a poor baseline walk test are going to have a worse follow-up walk test. And we're also giving a better basis for things like treatment effect heterogeneity. You can't really make sense out of heterogeneous treatment effect without really doing a strong covariate adjustment first. So the fundamental thing a clinical trial is trying to do is if you compare two patients who have the same baseline variables but were given different treatments, by how much better should I expect the outcome to be with treatment B instead of treatment A? That's the fundamental statement of what a clinical trial design does in a parallel group clinical trial. And so we need to use analyses that are consistent with that, which is analysis of covariance. If you have a continuous outcome and you have an R squared of 0.5 in predicting it using age and other things at baseline, you'll cut your sample size by 1/2. That's a very simple calculation. Change from baseline is a big topic that I'm not going to go into very much for time, but you have to know before you use change in baseline that it has like 5 major assumptions. You're assuming that the pre versus the post is linear and the slope is 1. That's what change from baseline assumes. And if you look in all the data sets you encounter, you'll almost never see that. You'll see regression to the mean that makes the slope less than 1. You'll see nonlinear relationships. So if you do a depression study and you do the Hamilton depression scale, you'll find that the baseline versus the follow-up is very nonlinear. So it doesn't qualify for a change score. So a post minus pre-change score is inconsistent with a parallel group design. And the change score is manipulated by patient inclusion criteria and regression to the mean. So ANCOVA is going to be the way to get around that. So it's another use of analysis of covariance. You have your follow-up value for your depression scale, and you adjust for the baseline without assuming the slope is 1, and probably without assuming it's linear. So the take-home messages are not to take sample sizes seriously. It's a game, and if we can ever get rid of sample sizes and use sequential learning, we'll all be better off. Alpha is not a relevant quantity to control or to spend. It's unrelated to a decision error. We need to choose high-resolution outcome measures. Longitudinal ordinal outcomes are general and flexible ways to capture severity and timing of outcomes. Always adjust for strong prognostic factors. And by the way, don't stratify by treatment in table 1. It's misleading to do that. And it leads to bad behavior on the part of readers. But that's for another day. So some references, and I really appreciate again the honor of being chosen to be the lecturer this year. Thanks for listening, and I'm really looking forward to the discussion. I hope I've managed to make everyone just a little bit upset, but not a lot. So thanks.
You have your hands up.
Thank you so much. That was great, but a little disconcerting, which is, I think, what you wanted to do. So thank you. It seemed, should I use the microphone?
Yes.
Because of the, yeah. So thanks very much. It seems like, this is really interesting and novel. I think the challenge is getting, the community to buy it, right? So you do a trial and you show a result, but it's not done in the frequentist approach, or, and then they say, yeah, but, they'll say, if it's a company, they'll say the regulators are never going to buy that. If it's colleagues, it's going to be the same sort of discussion. So my question is twofold. Number one, how do you convince the community to buy it, to buy this approach? And number two, could you take a already conducted trial and reanalyze it using this sort of approach and validate one against the other, and has that sort of been done so that you can say, well, we all know that statins reduce cardiovascular events. Let's take a statin trial and analyze it this way, all the data, and see what we get and how fewer patients we would have needed, et cetera. So it's the same question asked in sort of two different ways. One is validating it, and the second, how do you convince people?
Yeah, and there's multiple angles of attack. And so one of the difficulties in validating something is you have to know the truth. We do know a lot about statins, but what I think would be a little more interesting and definitely easier would be to use a Bayesian approach to re-execute a clinical trial to see how early you would have known what you need to do. So if you were to use a Bayesian approach for ISIS-2, the classic teaching example, you would have stopped about 1/10 of the way through that study. And you even raise ethical questions about it being a 25,000 patient trial that went to its conclusion. But in other settings, we do simulations, but there's a lot of papers out there that are reanalyzed trials that were originally done with the traditional approach. Some people are impressed by those papers. Some people are tired of them and saying, why don't we just design something prospectively and use that? So there's a lot of initiatives going on at FDA. And I don't speak for FDA at all, but I work for the director of drugs 1 day a week. So it gives me an opportunity to develop a lot of case studies and to help other people who are developing case studies with Bayesian approaches. So there's a lot of stuff going on, and FDA has a new initiative called C3TI, which is a clinical trial innovation initiative. One of the 3 projects in that is inviting pharmaceutical sponsors to submit secondary Bayesian analyses for live studies that were designed non-Bayesian, so that we can do the Bayesian in parallel and synchronously with the one they already designed. So there's none of that gets exactly at what you want, but I think it's all related, and there's many ways to proceed. And I think the biggest thing, though, that is if you think of Bayes as a problem-solving machine, that's the best way. So what I do is spend a lot of time dealing with multiple endpoints. I'll talk about that a little bit tomorrow. And how do you deal with multiple endpoints in a rational way instead of the ad hoc way that we do with traditional clinical trial design? That's just one place that's especially good for showcasing Bayes. I want to know, did this drug either reduce mortality or it benefited blood pressure a lot? And if it didn't do that, it made people able to exercise way better. That kind of thing.
Thank you for fantastic lecture. My question is related to stopping trials earlier with this method. Given you're looking at both efficacy and safety outcomes, and knowing that early on in trials, there's an overestimation of treatment effect at the beginning. So what's the best approach to deciding, okay, I've done this interim analysis and I've met my probability of this outcome and therefore stop? So are there stopping rules? And if there are not, how do you determine when to stop the trial?
And so there's a lot of elements to that. It's a fantastic question. I have a kind of a detailed clinical trial simulation in my Bayesian course notes that is under this next to last point there. And what happens with Bayes is sometimes you can stop earlier for efficacy. But way more often than that, you stop earlier for inefficacy. And so there's a problem if you were to stop early for efficacy, but the safety profile needs a longer follow-up. I think that's what you're getting at. That's a real difficult problem. But in the more frequent case where you stop early for inefficacy, you don't care if it's safe or not. You just want to get out of there.
I have a question about the ordinal logistic regression. They do have model assumptions, right? So the outcomes, they have to be some sort of proportional. Is that, can you explain how you actually make sure that assumption met, and then the way how you define the ordinal outcomes?
Yeah, I've got on my blog, which is the second URL, there's multiple blog articles that go exactly into that in gory detail. So just get under that blog site and there's keywords ordinal and you'll get a whole lot of things. But the basic idea of an ordinal variable is, let's say you're calling the categories A, B, and C, so we don't get confused by spacings. It doesn't assume spacings, but it assumes that an odds ratio for, say, for getting a level C outcome, the odds ratio for treatment is the same as the odds ratio for getting a level B or C, either or outcome. And so you definitely have an assumption to make there, but the beauty of it is if the assumption is false, the proportional odds model still tells you which treatment is better. So it always agrees with the Wilcoxon test. So if you trust the Wilcoxon test to say which treatment is better, did patients on treatment B tend to have better outcomes than those on treatment A? The odds ratio from a proportional odds model will always give you the right answer for that, even if you have severe lack of fit. What happens in statistical models very often is your main model parameters are pretty robust, but the standard errors are not. So if you have a severe lack of fit, you may not be able to use the same standard error formula that we normally use. But odds ratios themselves are still not misleading. The what? And I'm talking about the estimates.
Do you think the estimates still be able to tell the difference between the treatments?
Yeah, the estimated odds ratio is a simple function of the concordance probability. If you, Wilcoxon, all possible pairs of patients, one who got treatment B, one who got treatment A, what's the proportion of the times the B did better than the A?
Okay.
That's a simple function of the odds ratio, whether or not proportional odds is satisfied. And the odds
Frank,
ratio is 1 if and only if the Wilcoxon test statistic is 0.
Frank, that was actually very beautifully done. Now, my question is related to Hetzel's question about how do we convince the community that this is a much better or more efficient way of doing things when many programs that train statisticians, they don't even teach Bayesian, right? It's very, very few schools that would even have a course on Bayesian analysis at the graduate level, let alone in the undergraduate level. So there's not enough people trained in the methods
Yeah.
to be able to actually train the rest of the people, let alone to try and campaign and convince everybody that perhaps this is a much better way of doing things. Like, how do we change the system of training people?
Oh, you've identified a key problem because all of our graduate programs, except one at Duke University and Carnegie Mellon and very few other places, are making the mistake of perpetuating the current system and are not teaching. And I heard the worst thing about University of North Carolina, our alma mater, is the median student going through there gets not a single Bayesian course anymore, not a single course. This is criminal. We can't let that happen. And it's not going to improve the situation. But what we can do is to make more teaching materials, to make it more irresistible. The software world is revolutionizing Bayesian. If you look at what's happening in software like the BRMS package in R, which I had nothing to do with, it's revolutionizing Bayesian analysis. And so we're seeing obstacles removed, but we have to get people used to it. And to show that it solves problems is a key way to do it. But there's reason to be pessimistic and reasons to be optimistic. But the other thing is when on a bad day, I remember what the physicist Max Planck said. He said, people don't change, they just die and they're replaced by the next generation. They're replaced by the next generation. That's all too true. It's all too true.
Maybe if I can follow up on that a little bit. So most of us were trained not Bayesian,
Yeah, me too.
including us, right? So what should we do with the statisticians that we have? Do we have to be trained as Bayesian and forget our frequentist modes of action? Or can we do both? Or should we only go in one direction?
So there is a force in the world that many of you don't know about. This is a true force. His name is Richard McElreath, MC capital ELREATH. He's an anthropologist at the Max Planck Institute in Switzerland, maybe, or Germany. So he's not really trained as a statistician, but he's probably the best statistician in the world today. And he wrote a book called Statistical Rethinking. So this is a first graduate book for statistics that has no frequentist ideas in the entire book. So he shows what would happen if you started over. And this book is a work of art, and he has extensive YouTube videos. His lectures are some of the world-class lectures you will ever see. He puts his heart and soul into constructing these lectures and animating various concepts. So look up Statistical Rethinking by Richard McElreath.
Is it accessible to non-statisticians?
I would say pretty much. And then the other thing to look at is the life's work of David Spiegelhalter at Cambridge University. So David Spiegelhalter has a lot of very accessible stuff. He has a book on Bayesian methods in health research that's fantastic and very accessible. So there's some resources out there that are just game changers. But Richard McElraith is doing amazing good in the Bayesian world.
When we have a lack of prior information, then would it be correct to say that Bayesian approach and the classical approach will produce exactly the identical result?
They'll be drastically different. And the reason is the Bayesian probabilities are directional. So that's one reason. But the biggest reason is, let's say you do the simplest thing, you flip a coin until you get 10 heads, or you flip a coin 20 times. But let's say both of those experiments came up with exactly the same data, you'll get different p-values from those. Same data, different p-values. One uses a negative binomial distribution, one uses a binomial distribution. Bayes will give you one answer to that. And so, now I forgot how you started the question.
It's like I was asking, like,
Oh, yeah.
Yeah.
And so that's a simple example, but the other common example is when you do sequential analysis, the two will greatly disagree with one another. So when people say that you can get similar answers for Bayes and frequentist, well, that's true if you're going to be like unidirectional for frequentist and you have one look at the data. Once you have more than one look at the data or you do adaptation, everything diverges.
so you recommend still using Bayesian approach when we don't have any prior information?
You always have prior information. So I'm going to show an example where we were doing randomization and we think the randomizing software is defective.
Mhm.
So how do we calculate the probability that it's defective? So we have prior information there, which is if it was defective by more than 10% on a one-to-one randomization, somebody would have found it during testing. So that's our prior information. You always have prior information. If you have a treatment that's not curative, but it is palliative, you know the odds ratio cannot be 0.
Hmm.
It's impossible. The odds ratio is going to be a lot closer to 1 for incremental therapy, but if you have curative therapy, the odds ratio can be 0. So that goes into your prior. So you may not have any data, but you have ideas. And the prior serves, as Richard McElraith describes, the prior serves as a restriction. It doesn't always serve as data, a knowledge from information, but it serves as a restriction. It's a constraint. So if you use a maximum likelihood estimation for a logistic model, you're saying to yourself, all odds ratios are possible, even 10 to the 10th power. How would you ever believe an odds ratio of 10 to the 10th? But if you're using a flat prior and you do a simulation, one of the odds ratios you may draw in your simulation is 10 to the 10th power. So we always have some information.
Okay, thank you.
So you say that one of the reasons we have frequentists a lot is because Sir Ronald Fisher was talking about this.
And he hated Bayes. Absolutely hated it. Yeah.
He hated it. So that was a good thing because, you know, the famous incident that gave rise to the Fisher's exact test with the lady tasting tea. He calculated the probabilities based on if I give you these many things.
Yeah.
What if he had done it sequentially? If he had actually said, I'm going to bring you the tea with milk, with milk with tea, but sequentially, if I get the number correct, mistakes that you do, we may be Bayes.
So Stevenson has analyzed this. And what Steven said is that from Fisher's published data and in his record, you cannot reproduce the p-value that Fisher got because Fisher never told you the design. You can't calculate the p-value. You don't know if the lady was testing until she got 5, where the milk was first, or was she testing 10 no matter what she was going to say. You cannot calculate the p-value from Fisher's setup.
Last question.
Yes, last question.
Okay. So my last question is regarding non-inferiority trials, and where one significant challenge is the issue of non-inferiority margins. Do you think, like, with this approach, then that kind of solves the problem because you don't have to pre-specify a non-inferiority margin? because then you can look at the probability of different levels of margins for different populations using the same.
That's mainly it. And so, and the other thing is when you can use the same model, the same parameter distribution from your posterior distribution to give evidence for efficacy, similarity, non-inferiority with different margins. You could give 10, 20 different posterior probabilities. And you don't really have to be so firmly tied to a margin as people are in the frequentist non-inferiority studies. I did want to steal a minute and tell a story if I could. So one of the other secrets to your career is what collaborators you get to work with. And I've been blessed to work with some incredible collaborators that had really open minds. And one of the groups that I'm most high on, who I only got to know in the last 5 years, is at University College London in cardiology. They have this research group called Orbita, led by Daryl Francis and Rasha Alami. And I've got to work with them on several papers and help them design studies. So one of their most recent publications used the ordinal model with 74 levels because you have daily angina history for patients. They have a device that they're recording angina episodes overridden by a heart attack and death. So 74 levels, daily data for like 30 weeks or something. It's the power of the analysis was you couldn't believe the power of the study using the raw data, using the methods we had. But what really was cool about the group, when they submitted the article to Lancet, we had one non-Bayesian analysis for one of the secondary outcomes. And we were thinking Lancet would put a hold on this thing because it was so out there. I mean, it used the latest ordinal models, it used Bayesian design, and the Lancet reviewers said, you've got a frequentist analysis in this paper, you need to take it out because you need to have Bayes for everything. So that's when I know there's hope. But this group of investigators at University College London, they've been like a dream team to work with. They're open to anything. And one of the secrets, though, is they self-fund almost all their research. They don't, because they do things that nobody will fund. They do sham coronary revascularization, like sham stent. Half the patients get a pretend stent. And then, so they're the only group that's ever done a placebo-controlled angina outcome study in cardiology. And no company would fund that. And so they find a way to self-fund it and they do it the way they wanted to. But they're an inspirational team. So you ever look up some of the publications under Orbita from UCL, they're inspirational.
Thank you for that.
Thanks for having me. So you know that group?
Yes, Rachel Levine is joining us on a global cardiovascular analysis. So far, so good.
So on behalf of.
Yep. Can you have a picture? Very good, thank you.
Oh, man.
Who else? Yeah. Yeah. This week's one, two. It's not.
Thanks for attending. So what? Oh, yes.
Well, mine is usually very simple. It's just to say thank you. You know, one of the wonderful legacies that Janice left us is the legacy of kindness. Those of us who are privileged to work with him, she was one of the most gentle souls, but incredibly kind. And every time when I see one of their best friends, Jackie, I always, remember how the two of them were inseparable. But always exhibiting that, kindness and generosity. You would never know that Janice was one of the most brilliant people in the room. And yet she was always so quiet, humble, but incredibly kind and generous with her time and how she supported other people. So we're incredibly fortunate to have had the privilege of working and knowing her. For some of us who did, I often say I'm one of the luckiest human beings in the world because I got to supervise her, even though she may actually have supervised me. Right. So, all right. So we do this every year since Janice passed away, and I often really thank the PHRI leadership, Harrell, and you guys have been true to what we all try to do to honor Janice, to rally forces that this is one of the special events for PHRI because of what Janice meant to all of us. And I thank the leadership for PHRI for continuing to support this event and prioritizing it on top of many other things that take place at this in this area. And I always thank everybody who comes because without people attending, this event wouldn't be as special. So thank for all of you taking the time. I know some people have to travel long distances to be here and so on. But I have to actually first thank Frank for taking the time to be here with us. Janice was a fantastic teacher. And what we've all tried to do is to bring people who would actually embody that excellent teaching. And I hope you'll all agree that Frank was a fantastic teacher today. Let's thank him. We often try to invite Janice's husband, David. He was supposed to be here. Hope maybe he's online. I just also want to thank him for always, paying attention to this event, and their son, CJ, as well. So we are grateful for, the privilege of having worked and lived with Janice as well. And I want to also thank Gessel and Shrikant for you guys, doing all the planning to make this happen. And there's a lecture committee. I'm not sure whether I think some of them are here, who actually organize this event every year. We're very grateful for that. But the person who really makes this happen behind the scene is Tina. Yeah, believe it or not, Tina always makes us all look good, like we know what we're doing. And we're very grateful for Tina for always taking the time to make sure everything goes well and doing the logistics. We're very grateful. If anything goes wrong, it's usually not because of Tina, it's because some of us are not paying attention to what she tells us to do. All right. And I have to thank Stephanie Nis as well, because she really helps setting up, she's right there. Right. The technology and so on. And what's your name? Clarissa. Clarissa actually is the person who documents history. And she's always taking pictures of this event as well. And we're always grateful to everybody's input. There's lots of people who actually sponsored this event. Roche is one of the sponsors every year. They've been incredibly generous. The HHS Volunteer Association, they provide the catering for the reception, which please, there's a reception immediately after this. And then what else do I thank all of you for coming, and please make sure that you stop at the reception because that took a lot of love to prepare it. And we will be looking forward to the next Janice Pogue, which will be next year. If you have speakers who can actually teach us something we don't know, please don't be hesitant to suggest names. We're always looking for exciting speakers who can do what Janice would be doing for us. I hope you all have suggestions that you can put forward. But I want to thank all of you for really taking the time at the end of a long day to make this special for every one of us. Thank you.